thank you again to the organisers, to Paul and to Mark for setting everything up here. And so this talk here is inspired by, when I actually checked the exact quote, it was slightly different from what I thought. There's the great science communicator Carl Sagan in his TV show Cosmos in 1980 came up with this quite a startling quote that people have remembered for a long time. The cosmos is also within us. We're made of star stuff. And this series has been recently rebooted in recent years. So to test Carl's claim, what we can do is look at the human body and look at the proportions of the different elements that an individual human is made of, and then compare that to the wider planet Earth and to the Sun and to the solar system and to the wider universe, and see if what he says there makes sense. So by mass, we are almost entirely carbon, oxygen, nitrogen and hydrogen. So the majority of our bodies is water, and so by mass, oxygen then is our prime component. So carbon, nitrogen, oxygen, and those three species come up a lot in this talk, along with the hydrogen. And so then we have all these different other trace elements that go up to make the different percentages of our bodies, and indeed all of life on Earth. And so the first surprise then, if we can compare ourselves to our own home planet, Earth, our bodies are a majority water, but the Earth is absolutely not. Here is a picture. If you were to gather up all the oceans on the world and wrap them up into a small ball, that's how big it would be. So the Earth is almost entirely not made of water, despite our immediate experience that we live in a rainy part of the world. There's oceans everywhere. 2/3 of the Earth is covered by oceans. When you actually gather up those oceans, they amount to very little in terms of volume, because the oceans are relatively shallow compared to the diameter of the Earth. So we can also then compare to the wider solar system, and here's a scale model of all the different planets. And they're gathered into sort of useful arrangements here. So the Earth is there, the largest of the 4 rocky planets, and then we have 2 very, very large planets, Jupiter and Saturn, and then we have 2 intermediate planets, Uranus and Neptune. And if we go away and look at the composition of those planets, we can start to see what our solar system is made of in terms of the planets. So Mercury, the letters here are the planets. Mercury, Venus, Earth and Mars are the small rocky planets made mostly of metal and rock. So remember that small amount of water. So to first order, the Earth contains almost no water. It's just metal and rock. And then we go further out, and Jupiter and Saturn have little bits of rock and ice, but they're mostly hydrogen and helium, over 50% hydrogen and helium. And then further beyond, Uranus and Neptune are what we call ice giants. They're made almost entirely of ice. And those ices are actually hydrogenated versions of those 3 molecules that our bodies are made of: carbon, nitrogen, and oxygen. So it's methane, ammonia, and carbon, nitrogen, water, of course. And Pluto is kind of dead to us these days. It's no longer a planet. So it's now a dwarf planet. So moving on, so there's the solar system, and this is quite a neat arrangement. So our 4 rocky inner planets, and then beyond that we have our 2 very large planets, the gas giants, and beyond that the ice giants. And the way the planets have arranged themselves like this is entirely due to the temperature of the disk from which the planets form. So the inner regions of the disk, and I'll show you about that later, were warm and hot even, and just beyond a point where water can exist as a solid, then beyond that point you can very rapidly gather large amounts of material to you. So of course the solar system is dominated not by Jupiter or Saturn, let alone the Earth. It's of course dominated by the Sun. So the Sun is 1,000 times more massive than Jupiter. Jupiter is 300 times more massive than the Earth. So in order to understand the universe at large, and we have to start with stars, because the Earth is really a microscopic amount of material compared to the amount of material contained in stars. So we want to know what the stars are made of. So if we look at the Sun, we can take a spectrum, and here's a very highly dispersed spectrum of the Sun, and we can see these dark bands everywhere, which are absorption lines due to the different atoms and ions in the outer atmosphere of the Sun. And if we do that, we can compose, if we do that for the Sun and for gas clouds and for the wider universe, we can compose an astronomer's periodic table. For our dean is a chemist, so here's the astronomer's periodic table. It's basically hydrogen, helium, and a few scrap other elements. And the size of the boxes represents the relative proportion of the amount of these materials in the cosmos. So carbon, nitrogen, oxygen, there they are again. There's the three most common things in the universe after hydrogen and helium. So we see straight away that the surface of the Earth we live on and the Earth itself is not representative of the universe as a whole. The universe is almost entirely hydrogen and helium. And then there are some other important elements there like silicon and magnesium that form rocks. And then there's the iron there, Fe, that forms the core of the Earth. So magnesium, silicon and iron probably, and along with the oxygen, probably form most of the Earth. So the sun is just a very ordinary star. So how does it shine? And we've got we can go to chemistry first of all and say what if the sun is just a burning lump of coal or something, some very high yielding chemical reaction. If you look at rocket fuel, it can I think it's 10 to the 4 joules per kilogram you can pull out of rocket fuel. So if you can go for the highest yielding chemical reaction you can think of, could the sun just be a burning ball of chemical reactions? And the answer is no. It just wouldn't last very long, a few thousand years. Just nowhere near long enough. It just wouldn't work, quite apart from the composition being all wrong and quite apart from all of that. A much more subtle idea is what if the sun is shrinking? What if the sun is shrinking? If the sun shrank by a tiny amount, the release of gravitational potential energy as the sun changed radius by a tiny amount actually releases a prodigious amount of energy. As stars shrink, they heat up and radiate. And this sounds maybe a little bit implausible, but it's actually a perfectly reasonable mechanism, the release of gravitational potential energy. And in fact, some stars do shine by this method, protostars. And it was a big argument in the 19th century between Darwin and Kelvin over Darwin and Kelvin over the power source for the sun. Darwin and Kelvin said it has to be this shrinking star mechanism, but it only works for about 10 to the 7 years, 10 million years. And Darwin, theory of evolution and the fossil record pointed to billions of years for the age of the Earth. Something was horribly wrong. So Kelvin did admit, he says, well, unless there's some other power source we've not thought of. And of course, we'll come to that. So, but protostars do shine this way. So this is a perfectly, so Kelvin's ideas were perfectly right. And if you go to a cloud of gas that's forming a star and tune to the infrared part of the spectrum, you can see protostars radiating in the infrared part of the spectrum, deep in the cloud from which they formed. And in fact, they tend to even be more luminous than the star they finally make in the end. So that shrinking star mechanism works. It just doesn't work for long enough. So of course the answer is nuclear fusion is what powers stars. So 4 protons come together to make a helium atom, and there's going to be a difference in mass between the protons that make the helium and the mass of the helium itself. And that mass difference, through the most famous equation of them all, E equals mc squared, gives you the energy released. And when you do that and you work out the mass of the sun and you compare it to the present day luminosity of the sun and work out the kind of time you've got, you would only need to convert 10% of the mass of the sun to energy to power the sun for billions of years. So this is the way. And here are the reactions, just done out schematically here. So the reds are protons. So the very first step is the slowest. And the first step to make a deuterium, releasing a photon and a neutrino, and our keynote speaker will tell us all about neutrinos later this morning. But as you bring together two protons to make this deuterium, that's the slowest step, and it's that step that moderates the whole lifetime of the star. It's an extremely slow step, that very first step. And if that step was any faster, stars wouldn't exist for geological periods of time. And they build up to form helium, so 2 helium-3s come together to make a helium-4, and you get a couple of protons back. So that's how stars work. And so as astronomers, then we never mind just the sun, we want to look at lots of stars. And so we have this, so here's a beautiful cluster of stars. But of course, one never knows whether one's looking at a bright star or a star that's far away or a star that's near. And you have to sort out the distances. That's a whole topic in itself, to work out the distances to the stars. But in a cluster, you can kind of hope they're all at the same distance. And if you do that, you can plot them on a famous diagram, the Hertzsprung-Russell diagram. And what we have here is the temperature temperature, surface temperature, the effective temperature of a star versus the luminosity of the star. And you can see that stars live in just 4 places. The main sequence is where 90% of stars live. Our sun is on the main sequence as a yellow star around 6,000 Kelvin. And there are 2 other places that are important for our story of where the heavy elements that make the atoms on the Earth and in our bodies, where do they come from? So on the main sequence, you are fusing hydrogen to helium. And then something different happens then as you move to the giants, supergiants, and the white dwarfs. So if we look at the proportions of that, what that diagram can't show is that the numbers of stars change very sharply with the mass of the stars. For every one star that's 10 times the mass of our own sun, there are 1,000 stars like our own and 10 million what are called red dwarf stars. So the universe is almost entirely made of red dwarf stars. So what can we say about them? Actually, not very much. The nearest star to the sun is a red dwarf star, as you'd expect from those kind of statistics. So red dwarf stars are dotted everywhere. You can't even see the nearest star to the sun with the naked eye. They're so faint, but they are everywhere. The thing is, they will last, when you do the calculation, they will burn hydrogen on the main sequence for 1 trillion years. And the universe is only 15 billion years old. So by some measure, the universe is still a very, very young place. Not a single red dwarf has ever evolved off the main sequence yet. And we can check that by going to a globular cluster. My colleague Ray Butler in Centre for Astronomy researches these. And if you plot that same Hertzsprung-Russell diagram there, the red dwarfs are all in the bottom right-hand corner, and they're not going anywhere for a while. And that turning off there is where the curve moves away from the main sequence. That's what we want to look at next, because this will be the fate of the sun. So the sun has been burning hydrogen to helium for billions of years. And in another few billions of years, the hydrogen, there'll be a large proportion of helium in the core. So what happens next? Well, that shrinking star mechanism comes into play again. When you shrink a star, it releases energy, and that will heat the core. So the center of the star will compress and contract because the hydrogen burning is no longer providing a good pressure support. And in response, the outer layers of the star expand to balance this, because the star can't cool very quickly. So the energy is kind of trapped in a star on quite long time scales. And so the sun will become a red giant. So the sun will become a red giant that will be perhaps twice the orbit. There's the sun as it is now. It was already pretty big, and it will become twice the orbit of our own Earth's orbit. So the Earth will be destroyed by the sun eventually. Sorry for the bad news if you didn't know that. So eventually, though, the center of the sun will become so hot, 100 million degrees is what you need. The current temperature in the center of the sun is 15 million degrees, that helium will be ignited to fuse carbon. And there are other reactions. You could perhaps add another helium atom to form oxygen. And so your carbon, nitrogen, and oxygen are formed very readily in the center of stars like our sun. And what will happen later is every time your nuclear reactions increase, your center of the star gets hotter and smaller and denser, and the outer layers get puff out to be further and further away, and the outer layers expand. And so the star becomes a red supergiant. So we have the giants and the supergiants. And when you get to a supergiant size, the gravity of the star is no longer enough to hold on to the outer layers. And here's a spectacular image from a recently built telescope called ALMA in the Chilean desert, a millimeter telescope, where you can actually see the outer layers of an evolved star like our sun being puffed off into space. This is dust and soot being formed in the outer layers. So the temperature drops to maybe just 1,000 Kelvin in these outer regions. And deep convection takes place in the star, and it dredges up that carbon, nitrogen, oxygen, and many of those molecules that are so harmful to us that Miriam was describing, many of those are formed at this kind of phase. You form cyclic aromatic hydrocarbons, you make benzenes, you undergo combustion processes. In the School of Chemistry here we have a very renowned combustion centre, and the reactions they study there with or without oxygen are directly applicable to the tenuous outer atmospheres of these stars. So you get a very rich chemistry where you form dust and soot. By dust I mean silicate particles, magnesiums and oxygen particles, with some silicon perhaps, and by soot I mean sooty particles like carbon monoxide, and long chains, even things like cyanopolyions. And these are then ejected into space, and the star, you expose hotter and deeper layers in the star, and they ionize the surroundings. And if you go and look to the outer regions, you can see that these nebulae are often very sort of clumpy, and so you can shepherd these molecules into space. So the Sun will eventually become a white dwarf star, a compact remnant. So for low-mass stars, the nuclear fusion products are dredged to the surface and pushed out into space. Those solids are pushed into space. And those solids go a long way to explaining where the materials that form the Earth come from. So for more massive stars, these are those rare ones, they rattle through their nuclear fusion very, very quickly. Their nuclear reaction rates just go so much faster. They burn hydrogen to helium, then helium to carbon, oxygen, neon, magnesium, and so on. And there's a problem. When you get to, on this graph here, if you can, maybe it's hard to see, but the little spikes correspond to particularly stable molecules, atoms. You've got helium, carbon, oxygen. And if you add atoms together, you can release energy by nuclear fusion up to a certain point. And then on the other side, as in a nuclear power station, by breaking atoms up, you can release energy. And where those meet is iron. When you make iron, you can't get any energy back out by either fusing extra particles to it or by breaking it up. So you have a problem once you've formed iron. There's no more temperature available, and the star will has no more way to support itself, and temperature rises to billions of degrees. The photons disintegrate, and the nuclei you've been busy making all that time, and crush them all together, and you form a neutron star. And when that neutron star suddenly collapses, you get a huge change in volume, and all the outer layers all pile in, bounce off the neutron star, and form a supernova explosion. So there's the equivalent of a massive star forming like a planetary nebula. It's desperately shedding mass, but it won't be enough, and it will undergo a supernova explosion. And the best one we've witnessed recently was in 1987. There it goes in the satellite galaxy to the Milky Way. And we've been able to trace this over time. So the explosion illuminates rings of material around the center dot there is the supernova explosion, and you can see the shockwave hitting a pre-existing ring of material. And if you waited long enough over time, then the explosion would grow, and you'd see it in X-rays. This is one a few hundred years ago. There's the Crab Nebula, 1,000 years old. And eventually, you can see the material gets dispersed into the interstellar medium. And what you're dispersing into the interstellar medium is not only all the elements up to iron, but in that intense supernova explosion, what you're able to do is the energy available to you, even though they are endothermic reactions, you're able to generate all the heavy elements, all your gold, lead, all those heavy elements are generated in the moment of that explosion. And radioactive decay begins. So we can sort of put those two types of stars together in a sort of a cyclic kind of diagram here, where on the left we have the low mass stars that burn and form a planetary nebula and then eject their carbonaceous and silicate and dusty, sooty material back into space. And then we have the massive stars that undergo the supernova explosions that eject the heavy metals into space. And so again, I'm got too many slides, so I'll just show you a few more here. So if we go and scan the galaxy, we can actually see those subparticles blocking out the background light. There they are. Those dark patches are the agglomerations of those sooty particles in gas clouds. Here's a really nice example. There they are seen in silhouette. And if you go and look inside one of those clouds, you have to tune through into the infrared. There we are going through longer and longer wavelengths. You tune through, and so that shows you the size of the particles. Similar sized particles to cigarette smoke, in fact, to link into Miriam's talk. These are smoke-sized particles that are blocking background light. And strangely enough, to form a star, you actually have to start by being extremely cold, because you've got to rid yourself of all your possible pressure supports and throw away every form of pressure support so that gravity can get a grip. So I won't show the simulation there, but you can form a cluster of stars and if we zoom in, so forming a cluster of stars from a cloud, we can zoom into the most massive, and we start to see little distortions around some of the stars. And if we zoom in we find little disks. And these little disks are the disks of ices and dust and rocks that were formed that were formed in the atmospheres and the supernova explosions of the stars. And that's actually just an artist's impression of what you might see, but I must show you this image. This is a spectacular image from the ALMA telescope in Chile. It was $1 billion telescope, and this was one of the 3 design aims of the telescope, to take this image. What you're looking at here is a disk of material forming around a star that's forming, and those gaps are real. There's not an artifact of the telescope, and it's planets that you can't quite see that are hoovering out little gaps. And so you're actually witnessing the emergence of planets in a disk, planets that will go on to form a solar system like our own. There's an artist's impression. They'll draw material from their surroundings, and eventually we will form a solar system like our own. So back to Carl. So in summary, the rocks, metal, C, N and O atoms were all formed in stars. The hydrogen, though, in the water came from the Big Bang. So by mass, we could argue, yes, we're mostly made of star stuff, but there is a small twist. By the actual number of atoms in our body, if you add up for every water, there are 2 hydrogen atoms, we're actually mostly made from the Big Bang. Okay, thank you.
Thank you very much, Matt. Have we any questions?
Thanks for that talk, Mark. That was fantastic. You said there were so many red dwarf stars. Can they form planets? And since they last 1 trillion years, is that where we're going to find planets and life rather than looking for something?
Yeah, they certainly can form planets, but because they're so cool, the way the energy is transported through their atmospheres is by convection. And what that tends to do is tangle up magnetic fields so that they form star spots. And those star spots will lead to flares. And so it's thought that the environment around a very low mass star is actually quite hostile because the star is very flary. So the flux of, so you'd be bathed in, you'd be fried by radiation periodically. So yes, it is, it would, if life could form around red dwarfs, then it's everywhere. But it is thought you need a calmer star like our own sun, because our sun is hotter, and strange enough, that actually makes it a bit calmer, yeah, in terms of steady luminosity. Yeah. The photons, because the temperature is so high, billions of degrees, the photons become like little bullets, and they can photo-disintegrate the iron molecules. They just shatter them into heliums and protons. So the photons are so intense that they're able to just disintegrate the iron, the atom nuclei. They cause them to disintegrate. Sorry if I wasn't clear. Yeah.